Hey AP Chem, we are in the last section of Unit 2, which means that we are getting close to taking a test, which I know you're super duper duper excited about. So this test is going to be on things from everything from Unit 1 and from Unit 2. So that's all the stuff about particles, bonding, intermolecular forces, the whole shebang. So just be prepared for that. The last thing we need to cover are the different types of solids. So we've talked a lot about bonding. We've talked a lot about intermolecular forces, and so we're going to be talking about the different types of solids that you potentially could see based on all the stuff that we've been talking about so far. So when we talk about all the substances we've been talking about before, we've talked about ionic solids, and we know how they have a lattice, so we should be comfortable with that. But there are also these things called molecular solids, and I kind of alluded to them a little bit when I was talking about solubility, but the general idea behind molecular solids is they are the things that we can draw Lewis structures for. So we've been drawing Lewis structures for like things like carbon dioxide, things like iodine, that kind of stuff, things that are covalently bonded together. What ends up happening is that when we have a solid that's made of these types of molecules, you end up getting a lattice, like we talked about, that's held together with intermolecular forces. And those intermolecular forces are just those weak magnetic attractions that keep stuff stuck together. So what ends up happening is in the lattice, unlike an ionic compound where we have all of the different substances that are ion, 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 we have whole molecules in the corners there. And so their structure is just made up of molecules that are bonded together in a lattice. Not even bonded together, that's not correct. They are attracted to each other in a lattice. In an ionic lattice, it's a strong attraction, and in a molecular lattice, it's not exceptionally strong. What ends up happening is that there are not many free electrons in a molecular solid, just like in an ionic solid, because they're trapped in that lattice. And in the case of molecular solids, there just really aren't that many free electrons, period. So molecular solids are bad conductors of electricity. They also tend to have low melting points. They have strong bonds inside the molecules, but they do not have strong attractions between one molecule to another, and they tend to have kind of soft textures. So where I'm going with this is that at some point in time, you are potentially going to be seeing a question where you have a bunch of different substances and you'll see their properties, and you need to be able to identify, typically it's an ionic solid or something called a network covalent solid, which we'll be getting into in just a little bit. But properties that molecular solids have, they're bad conductors of electricity, they have low melting points, and they have soft textures. Unlike an ionic compound, which we've talked about before, that has a high melting point because they have the ions that are strongly attracted to each other. They are bad conductors of electricity as a solid, and they are generally brittle, but they have a hard texture. The other thing you will see here is that when you dissolve a molecular solid, it will not conduct electricity in any solution either, whereas an ionic compound will. Okay, network solids are a whole different kind of thing. So what happens in a network solid is that you tend to have nonpolar stuff that's in there, but what ends up happening is that instead of the substance being individual molecules that are attracted to each other through an intermolecular attraction, like an ionic attraction or an IMF, like London dispersion forces, what ends up happening is that these substances are actually bonded together. If you remember with intermolecular forces, I told you you cannot draw them as a straight solid line connecting two separate molecules because that indicates a bond. We had to draw the dashed lines. In a network solid, you want the line solid because it is a bond. So it's kind of a whole different ballgame there. So what you have is a big network of covalent bonds between the particles instead of just an intermolecular attraction. Network solids are typically brittle and non-conductive, so they break apart, but they don't conduct electricity, and that's because there aren't any free electrons. But what sets them apart from a normal molecular solid is instead of having the low boiling point and melting point, they have these kind of freakishly high melting points and boiling points. And that's because instead of having to come over those intermolecular force attractions, you actually have to physically break a covalent bond. And so that takes a lot of energy to happen. Now, network solids are unique, and you tend to see them in carbon and silicon compounds, or in carbon and silicon itself. So one example of this is going to be graphite. Graphite is pure elemental carbon. It's one of the ways you can find carbon. And in the case of graphite, what happens is carbon bonds to its neighboring carbons in 6 carbon rings, and they make what look like big honeycombed sheets, basically. And so what'll happen is you'll get these big layers of graphite that are covalently bonded to each other. And carbon only has 6 electrons. So in theory, its London dispersion forces shouldn't really even be that strong. But because of the network solid nature of this, where instead of this being a dotted line attraction, this is a straight up covalent bond, and it's very strong. So graphite is solid at room temperature, and it does a lot of things it's not supposed to because of its network solid nature. Now, graphite is actually used as an industrial lubricant, and the reason it is because it has these distinct layers. So it slides really easily over itself and other things, and it works really well to keep things lubricated, but without having to have like a liquid in there, because graphite's solid at room temperature. The other most common form of carbon that you're going to see is diamond. Now, diamond is also carbon atoms that are covalently bonded, but instead of them being in sheets that are flat, it forms a 3D lattice. So if you think about it, an ionic solid has a lattice where it's an ion and an ion and an ion, and then these things are attracted by a magnetic attraction. If I have a molecular solid, this would be a molecule, and a molecule, and they'd be attracted by an intermolecular force. But in a diamond, I have all these gray things here are carbon atoms, and then this is not an intermolecular attraction. This is a straight up bond. So it is a network structure, this huge kind of vertical lattice of different carbons. And because of this, diamonds are incredibly strong. So these covalent bonds make diamonds really strong. They have really, really high melting points, really high boiling points, even though technically it's just carbon and that's it. And the same thing happens with silicon-based compounds, so things like glass and stuff like that. Okay, the last one we're going to be talking about is metallic bonding. And metallic bonding is also kind of something that gives metals some unique characteristics. In theory, a solid metal that's just one type of atom should have only London dispersion forces, and so it should be relatively weak in its melting point, boiling point, that kind of stuff. But we think about metals, they're mostly solid at room temperature, and that's really different. Our nonmetals, those guys are all gases at room temperature. These aren't, but some of them have less electrons. So we got to explain that. And what happens is their trick is it's this thing called metallic bonding. So what ends up happening with metallic bonds is that there are attractions between the positive nuclei in the metals themselves that are strong and non-directional. And what I mean by that is that it's not like I have a permanent bond angle. It just means that generally they are all attracted to each other, and I can't pull individual atoms off easily, but I can move them and coax them in specific directions. What happens is that when we have metals, their positive nuclei are in a pretty fixed lattice. Like I said, it's kind of smushable, but in general, they're pretty fixed in their positions. But what happens is that they have a sea of electrons. So the electrons that are around the outside here, and this is especially important with the valence electrons around them, the electrons are very mobile. So if let's say I have one atom of aluminum here and another atom of aluminum here, the valence electrons don't necessarily have to stick around the aluminum that they came with. They are free to move around. And that's why metals are so good at conducting electricities, because they have this free sea of electrons to kind of work with. Those seas of electrons make it good conductors of electricity for metals, also good conductors of heat. They are malleable, which means that I can hammer them into thin sheets. They are ductile, which means you can draw them into a wire. If you think about all the wiring in your house, it's usually copper. Copper can be drawn into a wire. And because of that, strong kind of non-directional attraction that's happening, it also makes them have higher than expected melting points and boiling points for something that's a pure substance, because normally we'd think it would be something like like our nonmetals that we typically see. Okay, so like I said, when we look here, you can kind of see your core electrons are relatively fixed, but your number of valence electrons will kind of fly all over the place. And the more valence electrons a metal has, the more conducive it is to those metallic characteristics. So something that has one valence electron that's really tightly held onto, let's say like lithium or sodium, is not going to maybe be as metallic in character as something that has multiple valence electrons or has a larger size and the electrons are more free to move around. Within the metallic bonding, there are these things called alloys, and you guys are very, very familiar with them in your day-to-day workings, even if you don't know what they're called. So what alloys are metallic materials that are mixed by preparing two or more molten metals and then putting them together. So what you do is you take them and you mix them together. And they would be things like steel. It's probably the most important one for you. Brass, bronze, all that kind of stuff. Those are alloyed materials. So you can't just go out digging and find natural brass or natural bronze. That is a man-made substance, and steel as well. There are two types of alloys that we see, and they are called substitutional alloys and interstitial alloys. And you will need to know the difference between those. But if you understand what the name means, I think it makes the type of alloy easier to understand. Alloys are typically less electrically conductive, and we'll talk about why that happens in the next slide. They are harder and they are stronger than their parent metals as well, and they tend to be less malleable. So they kind of firm up, let's say, the different metals that you encounter in their pure forms. Okay, so a substitutional alloy. If you think about the term substitutional, it has the word substitute. And if you think about substituting, it just means you replace something with something else. And that's what happens in a substitutional alloy. A substitutional alloy is one where you have atoms that are close-ish to the same size. They have to be within 15% of each other's size. And you pluck out, essentially, certain metals and substitute in other metals into that mixture. So if we think about, this is an example of copper and nickel mixed together in this picture. If I had pure nickel, this would be all gray here. But what happens is when I alloy them together, and typically what we do to make that happen is you heat them up, melt them, and then mix them in a proper proportion. Sometimes the coppers will take the place of the nickels in the metallic structure. And then what ends up happening is that they kind of occupy that space and substitute out instead of a nickel or whatever you're mixing it with. What ends up happening is, if you think about all of the metallic properties that we talked about, they work because they have these kind of nicely similar sized atoms with the same number of electrons. When we take these alloys and then we change them by adding other things into them, it disrupts that. So if you think about how nicely this could bend, if these molecules or these atoms in here have to kind of move around each other, the fit just isn't quite as right. And so you get those properties where it's a little bit harder. It doesn't conduct electricity that well, that kind of stuff. So like if I take copper and put it in there, it's not going to conduct as well as, let's say, nickel would have. Interstitial alloys, on the other hand, are created when significantly tinier atoms are filled into the empty spaces inside atoms. So an interstice is just, it's the empty space. It's an empty space or a gap or an opening. So an interstitial alloy, what happens is that you have tiny atoms that fit into the gaps. And you can kind of see in this picture here, this example would be like steel. So steel is made with iron, which is quite a bit larger, and then carbon, which is tiny. And what happens is you mix in iron, you get it hot and melted, and you add carbon to it, and the carbon atoms fit into the little gaps in between here, and they cause a little bit of a disruption. And when that happens, it hardens things up. Because again, if you think about something being able to bend, these atoms in the gray here need to be able to kind of bend and move. But if I stick stuff into the gap, it makes it so it's harder to move. And that is an interstitial alloy. Okay. In this case, the solvent must be less than 60% the size of the solute. And I think I have that mixed up. So the solute must be less than 60% of the size of the solvent. So what I mean by that is these particles here need to be teeny tiny. Okay. They have to be, if they're too big, then it doesn't work. You can't alloy them together and it would be unsuccessful. The general purpose of alloys is to improve the properties of the individual metals so that you can use them for other things. Okay, we're going to do an activity based on this to give you some practice. And so if you have any questions, please make sure you get a hold of me. Otherwise, good luck.